So welcome back, everybody. Due to some unfortunate situations, we are going to have Zoom sessions Monday and Wednesday as well. But then next week, on Monday, it should be the 7th of February, we are going to be back all in person in the STEM building. And Friday, we will have the same setup as we had last Friday. So what I wanted to say a little bit about the plan for this week is to start with a more theoretical topic, and we are going to use the work energy theorem. So when we looked at the calculations of velocities and positions as we did in the previous 2 to 3 weeks, what we did was to start with the acceleration, and then we could integrate up and we would find the velocity as a function of time, and then we integrated up again, and then we found the position as a function of time. And then we could say something about the motion of a specific object. Alternatively, we could solve, as we discussed, couple differential equations. And if we couldn't solve them analytically, it's pretty straightforward to solve them numerically. Now, there are other ways to find, for instance, the velocity in case we cannot solve the problem the way we did in the previous weeks. And this goes actually through this work energy theorem. Now, this is also going to allow us to introduce concepts like conservative forces. We are going to look at the conservation of angular momentum. We are going to look at conservation of linear momentum. And we're also going to look at the conservation of energy. And these quantities which are being conserved have very, very important consequences for the analysis of a physical system. And they're also going to tell us a lot about the kind of forces which are at play when we are studying a specific physics system. So the kind of reading material which I normally recommend every week is now given by these sections in Taylor, 3.1 to 3.4 and 4.1 to 4.3. And we're going to dedicate some time to discuss these topics, energy, work theorem, as well as conservation of specific physical quantities. And then we're going to look at examples, and we're also going to look at in particular in the two exercises, the last two exercises, 5 and 6. So we're going to have still a mix of theory discussions, as well as we are going to look at specific examples, which are relevant both for the homeworks, but also relevant for in order to illustrate the theory which we are going through. Now, there is a lovely lecture online by Feynman. Actually, I misspelled it here. Sorry for that. And this lecture is something which I really recommend. And we are coming back to these topics about what are fundamental forces in nature and what are conservative forces and what are non-conservative forces. So this is something which is underlying all of the kind of physics analysis which we are going to do throughout the semester here. I also wanted to quickly remind you of some other practicalities. So if you go back to the basic GitHub address, you will also find the solutions to the homeworks. So if you scroll down and go to the right week, so when we had the deadline for homework number 1, you will find the solution to homework number 1, and the same thing with the solution to homework number 2. And they are all placed in this folder, which you see here, homeworks and solutions. And so we gradually put them in case you want to compare what you did with what we have placed as solutions. And if you spot errors, please do not hesitate to let us know. Okay, so I'm going to do a lot of just plain whiteboard work today in order to get started with the discussions of the work energy theorem. So we're going to switch now to the whiteboard immediately, and we will basically stay with the whiteboard. Now, if you have any questions, feel free to ask questions. Never hesitate, as always. So let's bring up the whiteboard then, and let's get a little bit started with the work energy theorem. And then we are going to look at some examples, and we will also look at we will try to get started with a discussion on conservation of energy, conservation of linear momentum, and other quantities. But the first thing we're going to start with is this work energy theorem. This is actually a very important theorem in physics. It's actually a statement. It's not a true theorem, as you may think from, let's say, from the typical way you would set up axioms and theorems in mathematics. But one of the things which is nice with it, it's going to allow us to find, for instance, the velocity as a function of position for a specific object, even in cases when we cannot solve the equations of motions the way we did it in the previous 3 weeks. So we are going to introduce the concept of work and energy, and the energy is going to be defined by what we call the kinetic energy, or the energy of motion. So let's now introduce the kinetic energy. This is the first quantity which we will look at. And we will define this with a letter K, the uppercase letter. And this is defined as 1/2 multiplied with the mass of the object and multiplied with the velocity squared. And the force which is acting on the system is a force which we assume can depend on position, on the velocity, and on time as well. So the force which is acting on a specific system, we just write this in terms of a vector, and this is going to be a function of position r, the velocity, and time as well. This is a more general type of forces. Now, later we are going to see that forces which depend only on the position, and this what we normally call the spatial degrees of freedom, those kind of forces, they're going to be forces which we will link with the concept of conservative forces, and these will be forces which actually conserve energy. And they are very, very interesting for us because they also link well with fundamental forces in nature. This is the definition of the force which we are going to look at. Now, if we look at the kinetic energy, if we now look at the term which goes like velocity here, if we stay with vectors, this is going to be equal to the inner product of two velocity vectors. And we are going to have an acceleration here, which is given by F divided by M. We assume also we are going to make an assumption now, and that is that the mass does not depend on time. So no time dependence for mass. So that means that the total mass of a specific system is actually conserved, and it doesn't change with time. So if we now take the expression for the kinetic energy, and I assume that most of you have seen this before, like in physics 181, so we don't need to go through the derivation of the expression for kinetic energy. So the kinetic energy is then equal to obviously mass times length squared divided by time squared, and that will be the typical dimensionality for energy. And this is the energy which is connected with the motion of the object. So what we could do now, and this is a scalar, keep that in mind because v squared is a scalar. So if we now look at the time derivative of kinetic energy, we said just now that the mass is time independent. So that means that there is no time dependence when we use the standard rule for it's not 1/2 divided by m, it's 1/2 multiplied with the mass. And now we have d dt. And what we need to do now is actually to calculate this quantity here. So if we now go back to homework number 1, and you may remember that there was an exercise 3 where we actually calculated this quantity. So now we are getting back to this homework and we see the usefulness of that specific relation. So if we now use what we had in homework number 3, exercise 3 in homework number 1, sorry, this is something which we can rewrite as 1/2 of m. And then we have dv dt times v plus v times dv dt. Now, if you look at this quantity here, we know that the product of two vectors, that is independent of whether we have v times dv dt. So these two terms which we have here, they can actually be lumped into just one. So we get a factor of 2, we get rid of the factor of 1/2. So this is something which we now can rewrite as m, which we assume to be time independent. And this is given by dv dt. And this is again multiplied with v here. Now there's an interesting connection which we can make. If you now look back at the expression which we had here. So this is a question to you guys, and feel free to answer in the chat or unmute yourself if you want to. If you now look at this term here, how can we actually rewrite this term? If you look at what we have here and the way we have defined the acceleration. So let me see now, there's an answer in the chat here. Let me just, that's the force. Excellent, excellent. So we can actually rewrite the term here, this specific term. We can rewrite that one as the force acting on the system. And now if you look at V, this is nothing but d of r dt. So it's the change in displacement as a function of time multiplied with a force. Okay, so this is just a rewrite of the equation. Now, if we now think of the way we have defined the derivatives, this is the so-called instantaneous derivative. So this is dk dt. So this is in principle given by lim of delta t. And then we would have the kinetic energy at a time 2 minus the kinetic energy at the previous time. And this would be a t2 minus t1, where we have defined this delta t equal to t2 minus t1. So if we now move on a little bit, we can now rewrite the equation which we have when we discretize. So this is the discretization, which we always end up doing. And that means that we are going to have a delta k, which goes over to a dk, which goes over to a delta k. And then we have a time, the infinitesimal time, small time, which goes over to a time step delta t. And then we do also have a d of r, which we would rewrite as a delta of r here. So if we now look at the equations which we have, if we stay with this expression for the force, so we can actually rewrite the force as well in terms of a delta v divided by delta t. But we can now keep this. So if we look at the terms which we have, we can actually rewrite this dk, dk dt is now going over to a delta k over delta t. And this is a quantity which we are going to, when we now set up the equations, this is going to be given by f times a delta of r times a delta t here. And what this gives us now is an expression which we can rewrite when we multiply away delta t. If we do that, because what we have done is actually, if you take this expression, this is the same as m times delta v divided by delta t times v. And what I did next now was simply to rewrite v as a, in term v over delta t as a dr, delta r times delta t. And then I can rewrite the expression which I have here for dk when I multiply away delta t. So sorry, this should be a delta k here, is now equal to this force which is acting on the system multiplied with delta of r here. So this is just a way to rewrite the change in kinetic energy. So what we can do now, if we look at the quantities which we have put in here, so we can set up a definition, and that is work done, this quantity which you see here. This, we define this as the work which is done by a force during a displacement which we call for delta of r. So we move the object a specific distance, delta r. And when we take the force and act on this specific displacement, this defines the work which has been done. And in our case, this quantity delta k, when we look back at what we defined up here, you see that delta k is just the difference between two kinetic energies. So we can actually rewrite this as the difference between two kinetic energies given by the velocity at the time t2, at an instance t2, at an instance 2, minus 1/2 times m times v1 squared. So v1 and v2 are now the velocities which this object has at two different times. And then this can now be related to this displacement of delta r. So the way you could now think of this, if we apply a specific force to the object which we have, you could now think of splitting this into different positions. We start at a position x0, we move to a position x1, we continue to a position x2, and this goes all the way up to a final position of x of n. So we are now defining this x to contain these specific positions, which you can think of observation of x2 all the way up to x of n here. And then for every small displacement, we are going to call this, since we are now dealing with a one-dimensional system, we are going to call this different distance between x0 and x1, x1 and x2. So we are putting up equally spaced points. We are going to call this displacement for delta x. And then what we have here, if you now think of this is the same as the force which is being applied as a function of x. So we have x on the x-axis. And in this specific case, we are applying a force which is f of x0. And then we have the next point, x1. And now we are applying a force which is given by f of x1. And this continues all the way till the final point. So this is f of x2 here. So you see now that this object which we are looking at, this f multiplied with delta r, and in our case, we are specializing to a one-dimensional case, this can actually be interpreted as an area. And this is actually the kind of interpretation which we are going to introduce now. So when we make delta x smaller and smaller, we will replace this summation of all the small delta x's with an integral. So this continues all the way to the final point here. So let me just write that one. So this will be a delta x again as a base, and then we have an f of x n minus 1 here. Now, if you look closer here, we could now think of the difference in energies. We could now define a delta k, which is the difference between the kinetic energy and the final point. And we write this velocity as a v of n squared minus 1/2 multiplied with v0, which we could think of as initial velocity. And this quantity here is going to be given by the sum from I equals 0 up to n minus 1. And then we have the forces, which depends on x of I, multiplied with this fixed term delta of x. Now, in the limit, so in the limit of delta x goes to 0, of this quantity I equals 0 of n minus 1 of fx of I of delta x. This is something which we now will replace with an integral from x0 to x, the final x here. And then we have d of x multiplied with f of x. And this is an integral. And we are going to define this as the work which is done by a force on a segment delta x from x0 up to xn. And this is now related to the change in kinetic energy. So this will now be given by 1/2 of n of v of n squared minus 1/2 of n of v0 squared. Now what you see stated here is actually the work energy theorem. Now, in this specific case, we had a one-dimensional object, but you can easily extend this to 2 dimensions, 3 dimensions, and so on. Now, if you now look at the expressions which we put up here, you can easily see from the graphical representation which we had here, that this is actually the definition of the process of integration when we let the delta x become smaller and smaller and smaller. Then we can approximate this sum over the forces, which are now the function values at the point x of I, multiplied with this small segment delta x. And this translates into an integral. So that is essentially one of the bases of integral and differential calculus. So that's the kind of way you can view this. And if you now think of this in more than one dimension, you can now think of a path, which we are going to call for C. So you could think of now you starting in a position R0, and then you have different measurements which you make along a specific path, and you end in a point R of n. And this is now given by this trajectory, which is chosen here, which brings you at the final point. Later, we are going to see that the total work which is done, if we have a force which conserves energy, it's going to be independent of the path. So this is an extremely important statement, which we will discuss a little bit later next week. But now we are just going to state it, that if you have a conservative force, then that will be independent of the path which we take. And normally what we have then, if we look at the definition, what we can rewrite this integral, instead of specifying a specific delta x, etc., we will simply specify the path which we are taking. And this is now given by the force acting on a specific line segment d of r. And that's the same as the change in kinetic energies. And now we're going to write this as an mv, and we can think of a final time, which we can write as an n here, minus an initial time, the velocity at an initial time, or just the initial velocity at the v0. Now, I want to ask you some questions now, just to break the monotony with me preaching all the time here. So if you look at this f times delta of r, can this be negative? And if so, what does that mean? So any good suggestions? Whether this is a quantity which can be negative or not. What happens if that quantity is negative? What would it mean? So let me see if it chat here. It can be negative. And what would it mean then? The work is, that could be one thing, that work is done in the system. But if you think in terms of the velocity, if that term is negative, yeah, it could be negative and would go backwards, or that the velocity is just reduced. So if the difference between the initial and the final velocity, yeah, or accelerate that direction at least. So when you see this term becoming negative, then it means that you do have a system where the velocity decreases and the kinetic energy just decreases. So that's one way to interpret it. So let's put up the next question then. Suppose now that the force is perpendicular to the displacement. So suppose now that we take this force and we have the force which is perpendicular. So this is a sign for being perpendicular. So which means that if I take F times delta of R, that is equal to 0. What does that mean for the kinetic energy and the velocity? So any good suggestions what that could mean for the velocity which the system has? And obviously then the kinetic energy. Feel free to write that in the chat. So let me just state the question here. What happens to the velocity then? Yeah, excellent. To V, so the kinetic energy is, the change in kinetic energy is 0. And when a change is 0, that means that the velocity is constant. So what happens then is that this delta k, which we put up, is equal to 0. And that means that velocity is just constant. So there's no change in velocity here. So these are just some simple observations which we can make when we look at these expressions here. Now let's look at an example and take this as the first example here and go through that. So we would take the boring sliding block. So we have a block which slides back and forth in one dimension here. So it's fastened to a wall. And then we have a one-dimensional block here, and this can just move back and forth. And it oscillates back and forth, and there is no friction here. And what we said last week is that the force which acts on this object, and now I'm taking away the vector signs, because the force does not depend on any 2 or 3-dimensional quantities. So we can just put in constant scalars here. So F is equal to minus k times x, where k is the spring tension. And then we could now think of moving. We move from a position x0 to a final position x1. And then we have an initial velocity and a final velocity. So if we now look at the velocities which we have, so we would have a velocity at this point x1, which we just call v1, and then we have an initial velocity, which we just call v0 here. And if you use this work energy theorem, this is now going to be given by the integral from x0 to x1, and then I take my force here, minus k times x of d of x. And this is something which we can integrate up. And if we integrate it up, we get minus 1/2 of k times x1 squared, and then plus 1/2 of k times x0 squared. And now we can reorder this expression here. So if we reorder it, we can now put in the x1s and the v1s on the same side. So we would have v1 plus 1/2 of k of x1 squared. And this is equal to 1/2 of m of v0 squared plus 1/2 of k of x0 squared. Now, you've probably seen something similar like this. So what does this actually mean? Or what does it represent? What does it mean, what we have here? And how do we interpret, and what is 1/2 of k x1 squared and 1/2 of k x0 squared? What do they represent? So I see that somebody has already answered here. This is the total energy of the system. And so what you have here is the total energy of the system at the position x1 and velocity of v1. And then we have the same quantity there. This quantity here defines the potential energy. And as it's stated here in the chat, I don't know if you have all of you have the possibility to see the chat. This actually means that energy is conserved. And this is something very, very important. And we will see later that this type of force which we put in, this k times x, is actually a force which conserves energy. So one very important thing I want you to note here, let's put 1, energy conservation. Energy is conserved. So this is actually the total energy. And the total energy, I'm going to define that just in a moment. Energy is conserved. The total energy, the way we are going to define it, is kinetic energy is equal to kinetic energy plus potential energy, plus potential energies. And in this specific case, with the harmonic oscillations, this force F of x depends only on x now, minus k of x, has a potential or potential energy, which I'm going to write as a V. So I'm going to use the symbol V for potential energy. And this potential energy is given by 1/2 of k times x squared. Okay, so let's try to do another example, because I promised you that we could actually use this kind of machinery, which we do now with the work energy theorem, to actually find the velocity in case we could not integrate or solve the equations of motions as we saw in the previous weeks. So let's look at a new example here. And this is an example taken from electronics. It's a very simplified case. So let's look at that one. So this is our example 2 here. And this will show us how we can now find the velocity by just using the energy work theorem. So as I said, in case you cannot find the solution in terms of the solution of the integral differential equations or integrating up, this is another path to find the velocity. So let's now look at a simple system, again in 1 dimension. I never venture beyond 1 dimension. So you could now think of what you have along the x-axis as the surface of a material. And in every position here, so the distance between these 2 points is given by a variable b. You could think of you having an atom or a molecule or an ion in every such position. And then what we have now is an electron which comes in here, and that feels a potential, which is, or a force, which acts on this electron from the different atoms which are placed on the surface of this material. So you could now think of an electron coming in here. So what we are going to say now is that x0 is a known quantity, and we could put that one to 0 meters. We could also assume that v0 is known, so the object is at rest, 0 meters per second. And then we are going to assume now that there is a force. So this is a simple model, and you will see that this force depends only on some constant, and then it has a sign of 2 pi x divided by b here. So the sine function is included here in order to achieve this kind of periodicity, because these atoms, they appear in a periodic way. So you could now think the electron, when it moves here, it sees this atom first, and then it moves on and it sees the next one. And in between, it doesn't see a force. So this can be represented the way this force acts. It can be represented by some kind of sinusoidal or cosine function, which means that we have some kind of periodic force, which is just being repeated as this electron moves along the surface. So this is a very, very simplified model for a force which appears due to the motion of the electron close to a surface. Now, if we now use the work energy theorem, which I'm just going to shorten to WE theorem, work energy theorem, what we can do now, if we want to find the velocities, we know the velocity at the initial point, v1 squared minus 1/2 of n of v0 squared. So this is just simply 1/2, since we have chosen the initial velocity to be equal to 0. And this is now given by this integral, where we also chose x0 to be equal to 0. And then we integrate up to the point x1. And then we have an f0 times a sine. So this is the force which we are integrating up now, 2 pi of x divided by this b and d of x here. So this is our force times d of x. Now we can just make a change of variables, and then we have a 2 pi of x divided by b here, and we can then take a du, which becomes simply 2 pi times d of x. This is just a change of variables, which means in turn that d of x is equal to b times du divided by 2 pi. So these are just technicalities. And if I do that change, I can then easily integrate up, because you see that I have just a f0, this constant for the force, multiplied with sine of u. and multiply it with the u. And then I have this constant, which is b divided by 2 pi. So if I integrate up these integrals, so these are just the intermediate changes which I'm making to the integrand, then what I get when I integrate everything up, I get this f0. I have these constants b divided by 2 pi, because I make the change here and replace d of x with du, and I put u in here, and then I simply have an integral over sine of u times du. So what I have now is I have to include these constants, b divided by 2 pi here. And when I'm integrating up sine, I know that that is minus cosine. I have a minus sign in front of it. So I get actually a cosine of 2 pi of x1 divided by b minus a cosine of 2 pi of x0 divided by b. And I know that x0 is after all 0. So that means that the term which we have here, that becomes simply cosine of 0, which is 1. So what we end up with then is a simple expression which tells us that 1/2 of m times v1 squared is equal to f0 times b divided by 2 pi. And then I have my cosine of 2 pi of x1. This is an x1, the final position of b minus 1 here. And that means that when we now take the square root, we get that the velocity v1 is plus minus, and then I have the square root of f0 of b divided by 2 pi, and I have this cosine function of 2 pi x1 divided by b minus 1. This is actually one of the exercises which we are going to see in one of the coming homeworks. So these are just two specific examples which we looked at and how we can use this theorem. And the case which we had here is a case where we now had a slightly more complicated expression for the force as a function of x, and that would have made it a little bit more difficult to integrate up as we did before. So this is an alternative to solving differential equations and or to integrate up the acceleration when we have the force and so on. Any questions so far, guys? Is this pretty okay? So these are just examples of the applications of the work energy theorem. And you've probably seen something similar before. But now I'm going to state something which is going to become important for us. So this is the work energy theorem itself. But now we have a conservation of physical quantities. And we are just going to look at what we are going to call in a more generic way as conservation laws. So that means that specific physical quantities are independent of time. So we would see, for instance, that the energy, a typical thing, if we see that dE, the total energy of the system, as a function of time is equal to 0, then we would say that energy is conserved. If we have the linear momentum, so let's just set that one up, linear momentum, which we're going to define in just a few moments, P. If we have dP dt equal to 0, then linear momentum is conserved, or just momentum. So sometimes we're a little bit sloppy. Instead of saying linear momentum, we just say momentum. So in this specific case, then, we will say that momentum is conserved. And this allows us to say something very important about physical forces. So there are things which I wanted to point to you before we actually do any derivations. There are two important conditions on forces. And let's set these up without any proof. Two important conditions. So let's highlight these. And one, if we saw in the beginning here that we assumed that the force could depend on the position, the velocity, and time. But one thing which we can say now, if we can have a force which depends only on position. So that's only dependence on R. And you've already seen two cases which depend only on R. In both these examples, we have a force here which depends on X only. And we had another force here which actually also depends on X. And what we found here is that energy, we found a statement by using the work energy theorem that energy is conserved. The total energy, which contains kinetic energy plus potential energy, is actually conserved. So there's a question in chat here. Okay, so this is actually, oh, I may actually have forgotten. Yeah, that's a good point. That's a thank you, thanks. So I see there's a typo here. I actually forgot the m multiplied with 2 here. So if you look at the equations, I was a little bit too eager to write up the final equation. So there is a factor of 1/2, which I've forgotten. So if I multiply away this, we get rid of that one here. And there's a factor of m here, which we should have divided out. So actually, this expression, and this is actually correct in my notes, I actually forgot that. So we should take away, if you look at the denominator here, this should actually look like as m divided by pi. So this is actually me not reading correctly my own notes. Thank you for noting that one. That's good. So we have people with some eagle eyes in the lecture hall here. Thanks. I hope that helped. Okay, so there's a very important statement here. If we have a force like that, which depends only on the position, then the path chosen. So I'm going to put a 1 here. The path chosen in the integral for the work, in the integral for W, for W is equal to the force from a position x0 to a position xn of f of x d of x. This is actually independent, leads to a result which is independent of the path which we've taken. And we're going to show that next week, which is leads to a result which is independent of the path which we are taking. And that sounds very strange. So to have a force which depends on R is a necessary, but is not a sufficient condition. So this is also going to lead to energy conservation. But the important result to have this path independence is defined by the curl of the force. So let's set up that. So this leads to energy conservation if it's independent of path. And we will try to illustrate this in more detail next week. But now we're just stating that. To have a path independent work, then we have the important condition. What we need then is that the curl of the force is actually equal to 0. And we are going to play around with these kind of expressions again and again in the coming weeks. So if you have a force like that, like the gravitational force is a so-called energy conserving force. So these are normally called, if the force obey these two conditions, the first one is a necessary condition, but it's not sufficient. This is the important condition. then we would call these forces for conservative forces. That means that they typically conserve energy. These are called conservative forces. So we haven't derived this. For some of you, when you've been looking at the topics in calculus, when you looked at things like path integrals, when you looked at the line integrals and so forth, you've probably seen this requirement that the curl of the force has to be equal to 0 in order to obtain a result which is independent of the path you take. The simple example which we had with a sliding block was an example where we obtained a conservation of the total energy when we moved from a position x0 to a position x1. So what I'm just stating now are just these properties of conservative forces. And now what we are going to look at is conservation of specific quantities. And we are going to start with the first topic, which is often the easiest one to show, conservation of linear momentum. So we need some time to actually go through this theory, because this has so important consequences for what we end up doing in physics, and especially in classical mechanics. Yeah, so if a quantity is conserved, there's a very good question in the chat here. And the question is, if a quantity is conserved, does that mean it's conserved on all axes? For instance, if energy is conserved, does that mean that energy in the X, Y, and Z direction is also conserved? It would actually mean it may not be conserved in one specific direction, like the X direction, but it would be conserved in the total space, the three-dimensional space. So you could actually find a path in the X direction, which could happen, it couldn't conserve energy. But if you take the path with X, Y, and Z, then that will conserve energy if you have a conservative force. But you could construct this, actually you should, if you have a conservative force, you could just move along the x-axis and then along the y-axis and along the z-axis. So that would be just a random path you would take. And in that specific case, energy would still be conserved. So that means that if you have a conservative force, you can specify any path in space, in this three-dimensional case, x, y, and z, and you would still have conservation of energy. And it's a very important statement, because when the result is independent of path, what it means is that you can define any type of path in space. Was that what you were thinking of? So you could actually move along any axis here, in any direction you choose, and the result would still be independent of the path you chose. So it's a very strong statement. Did that help? Or no? Excellent. So you could go along any direction in X, Y, and Z, and the energy would still be a conserved quantity. So what we are going to look at now is the conservation of linear momentum, which is one of these properties which are very important in studies of physical systems. And when we are going to, for instance, write a program for the solar system, one of the tests you can make to see that your system is conserving angular momentum and linear momentum is actually to plug in a check like that in your codes. Because if you have an energy conserving force like the gravitational force, that is also force, when we only look at internal forces, which conserves linear momentum. In addition, it's a force, the gravitational force, which also conserves angular momentum. And these are quantities which we can check are conserved when we develop our formalism. So let's now, and I see that my time is running out here, and last week I actually stole 1 or 2 minutes from you, and maybe I should actually try to just end on time here today. So on Wednesday, we are going to look at conservation of linear momentum and conservation of angular momentum. I'm going to stop the recording now, but feel free to hang around because I will keep this window open till 5 o'clock if there is an interest. So I'm going to just stop the recording.